Hey everyone, welcome back to your channel PHYSICSSIRJEE, and this is Olympiad workout series, and we are going to take up the INPhO 2019 problem number 4 as promised in the previous video. Okay, so this was a question about a compressible fluid and its pressure variation inside it as a function of z coordinate in the direction of gravity. Okay, so this is for those who are watching it for the first time. I would request you to actually solve this problem. Unlike the previous INPhO problems, this is a very straightforward one. You need to just have some composure and a lot of marks actually for the kind of question this is. This is even at the JEE advanced level. Okay, so you need to be very good with your concept and also the free body diagram. Okay, so you want to give it a try. Pause the video here. Try it for not more than 10 minutes. You'll be able to get through it and then follow the solution that I'm going to present. It has two parts. First part has two questions in which you have 5 marks, and the second part, as you could see, is only 2 points at the end of the question. Okay, so let's go with the formal wording of the question. Consider a long narrow cylinder of cross section A filled with a compressible liquid up to a height h, while density rho is a function of pressure P as given. Rho is equal to rho naught by 2 plus 1 plus P divided by P naught. Obviously all these knots are constants. Okay, so the functions are rho and P, as you could see. And that is the basic idea of any compressible fluid. Whenever we are taught about incompressible fluids in fluid dynamics, we are told that the condition for the incompressible fluid is that the density should be uniform. And as you could see, that is completely gone out of window here, with density varying with z coordinate. Okay, the depth z is measured from the free surface of the liquid, where the pressure is equal to P atmosphere. One major thing you need to note, and a lot of silly mistakes have been done even for my students when they attempted this exam last year, was that when this P atmosphere is given, they try to substitute it for P naught. P naught is a constant, P atmosphere true. So these are two different constants that you should have noted. Okay, right. Obtain the pressure Pz as a function of z. Obtain the mass of the liquid in the tube. These are the two parts of the first question. Okay, whereas the second one talks about the liquid being incompressible, right? Assume liquid is, let's say, incompressible of density rho naught in a separate container. Then in that particular container, if you calculate what is the pressure at a function of z, and compare it with the pressure as a function of z that you obtained in the previous question, the difference in those values from the ideal liquid to the real liquid is being requested in the second question. Okay, so these are the questions. Let's attack it one by one. So I pasted the first question on the top, as you could see, and also the expression that was given in the question, I pasted at the bottom so that we can recollect it whenever it is needed. This was the rho versus P relation that was given. So what I'm going to do is, my idea was to find the pressure as a function of Z, whereas the rho as a function of P is given. So if I can get a pressure and density relation using free body diagram, I'll be able to eliminate one over the other. Okay, so for that crude diagram of that particular container, and at a distance Z from, can you see that? Yeah, at a distance Z from the free surface, if I pick a small fluid element, shade it, the width of that fluid element, let's say, is dz. On that free body diagram, there will be the forces of pressure from the top, that is P into A. This P is a function of Z, whereas the force from the bottom would be slightly more and would be called as P plus dP into A. This is a very familiar stuff to you. And the weight of that liquid is dm into G. So vector sum of all these three forces should balance out in equilibrium, and is what I have written here. Okay, right. Then this P and A and this part of P and A will get cancelled, and not only that, dm part of that rectangular thing or cylindrical thing can be written as rho at that place multiplied by area of cross section into dz. It's a pretty simple thing. Then from this also you can cancel out the area of cross section because it's uniform throughout, and this dp is equal to rho g into dz. Actually, even if it is not uniform, this area at that place can be cancelled. I think this is a very basic expression. Some of the students would directly write this. The pressure difference between two dz points would be directly related to rho g dz. This is true even in incompressible fluid. When you integrate this, then rho may not come out of the integral, is what the compressible fluid will talk about. Okay, so I rearranged because I'm hell-bent on replacing rho in this given equation at the bottom of the screen. Okay, so I wrote rho is equal to 1 by G dP by dz. Then I'll go ahead and substitute in that given equation. As you could see, this equation, I'd substitute for rho here on the left hand side, and this is what happens. Okay, right? Now I have a dp versus p equation. You all know what you should do. Bring all p terms on one side and dz terms on the other side and integrate. While integrating at z is equal to 0, which is the free surface, you have to substitute not p naught, it should be p atmosphere. Very careful. Okay, right? And at z coordinate, we need to know the value of p. Okay, so you get a logarithmic simple integration, and then we rearrange, you'll get a exponential function for the p of z with p naught and p atmosphere separately and carefully written, and this is p naught. And as expected, as you move down the z coordinate, there is an increase in pressure, but not linear in this case, it is the exponential term. Okay, so this is what the first part is. Now for the second part, where the mass of the entire liquid is considered. Okay, so this entire mass is being considered. Instead of taking the free body diagram of only differential element, I'll take the free body diagram of the entire liquid. Okay, so let's do that. So this is entire liquids FBD now. Entire liquids FBD, in which the top part would be acted upon by P atmosphere force, and at the bottom, pressure that you've got as a function of Z. I'll just keep it in your view. Yeah, this one. Z, you should substitute H, and that is what you are going to get the value for the pressure there, and that would be acting upward. So same logic. Now last time we equated dmg, now we'll equate mg to the pressure difference from top to bottom multiplied by area. This Z I'll substitute as H. So here I should have actually written H here. So let me correct that part. Yeah, this part should be substituted with that height H. So I've changed that. Okay, so this is the mass of the liquid that is available in that fluid of height H. Okay, slightly complicated, but I think that would be good enough for earning you points in the exam. Okay, so let's move on to the second question. This is the second question. So second question is a straightforward one once you solve the first. Okay, as I said, he will be comparing the pressure difference between a compressible liquid that you got in the previous problem to the incompressible liquid whose density is uniform and rho naught by 2. He chose that kind of a liquid, and he's also assuming the value of that constant p naught, we'll use it somewhere, is very large compared to this rho naught gz expression. Okay, so that means he wants some approximation. So what I did is, this first equation is the answer to the last question, right? So I just borrowed it into the screen. I borrowed and pasted this one also. It might be useful. Let's keep it here. So this one we all know, okay, is from the previous problem, and this is very simple. I think in an incompressible fluid, as you go down with height, pressure over the atmosphere increases linearly with density. So density into G into Z. So this is for an incompressible. I stands for incompressible fluid. The answer that we got previously and the expression that we know already, you subtract, you'll get delta P that he is requesting. And when you subtract, you carefully observe these yellow terms will again produce minus P naught minus P atmosphere, which can be taken common with this. So P naught plus P atmosphere, this term here minus 1, that means I have accounted for this, and this blue term will be minus here. Okay, right. And then what I did is I used the approximation that he mentioned in the question. Can you see this approximation means this power is very small compared to 1. E power x expansion, we remember, is 1 plus x square by 2 factorial plus x cube by 3. That thing minus 1 term goes off. So I wrote x plus x square by 2. I wrote up till 2 terms, and I say the higher terms can be neglected because of this particular expression. Okay, you might argue I would have retained only 1 term. Reason for retaining 2 terms instead of only 1 term is the presence of this z term. If this blue term were not there, then I would have just kept it as 1 particular term. So this is a very important thing that you need to know. Your degree of approximation, whether it is first degree or second degree, should depend on what terms it is having as a friend in that particular equation. Okay, so because it's already linear, I need to be safe side taking a higher term. If I had a z and a z square term, then I should write the third term as a z cube term. So I hope you got this point. So, and then I collected all the z terms at one place. This is very simple, and this term actually gets cancelled with this first product. Okay, so the blue term goes off. So I collected z term and z square term separately, and that is what I'm supposed to write. It is up to second order. You want higher orders, you can take higher orders also. So this is the answer for the second question, and it's a pretty straightforward question, only bulky calculation, but I think compared to the questions that we have done in INPHO in the previous videos, this is much simpler. Okay, so this is the next video we are going to take up. It is from the online physics Olympiad 2020. We have been doing some questions from there also. So I'll not read the question and spoil your experience. You just read the way the question is given in that particular exam, and I think you should be able to crack this question also. It's a nice question on a topic of friction, equilibrium, etc. So I'll not say anything further. Okay, so for those people who are watching this video for the first time, there is an Olympiad workout series which this one is part of, and there is a playlist in the link in the description below, and all the videos that you might have missed in the past are written in that particular playlist. You can go through all the videos so that you can gain a lot from them. Other playlists of this channel, if you are visiting it for the first time, apart from Olympiad workout series, is AITS select series, Pathfinder solution series, and the result series. All this, what are these and everything, are explained in those playlists, and the links of these playlists are also in the description below. So please do like, share, and subscribe to my channel, as the videos are coming thick and fast and in all the series. And even there is a JEE advanced papers questions that I am doing, previous year's papers, so that we can close in, especially for the JEE aspirants of this year. So do hit the notification bell icon so that you get the regular updates, as I'm going to upload more than one video per day. Okay, thank you for staying with me, and let's hope you come back for my next video. Right, see you.